Chapter 2 is going to focus on nomenclature, writing formulas, naming compounds. There's a part of Chapter 2 that we're going to pull out and focus on later that deals a little bit more with the specifics of atomic structure, early models of the atom. For now, we want to focus on just some general characteristics of bonding, how to predict what kind of bond will occur, and then eventually that'll lead us into nomenclature, which we need to master the art of writing ionic and covalent formulas and compounds. So before we go into the nomenclature, a quick review of bonding. Chemical bonds obviously hold atoms together. The purpose of a bond is to create stable atoms. A major misconception. Atoms are neutral. If you look on the periodic table, I think all of us remember figuring out protons, neutrons, electrons. Let's say we have a fluorine atom. We look at the periodic table, the atomic number of fluorine is 9. Fluorine has 9 positive protons. That's a positive. Since atoms are neutral, there would also be 9 negative electrons. The protons and electrons have to match up in a neutral atom. To figure out the number of neutrons, we just subtract the atomic mass and the atomic number. The atomic mass is really a combination of the protons and neutrons in the nucleus. Electrons are so small that they're really insignificant when it comes to mass. So if the mass of fluorine is approximately 19 AMUs, we would say there's about 10 neutral neutrons. So here is my neutral fluorine atom. The misconception: neutral does not mean stable. Fluorine atoms are neutral, but fluorine atoms are nowhere near being stable. They're highly reactive. Check this out. Let's see if we remember a blast from the past. I hate drawing atoms like this, but it might be kind of a good visual. Do you remember back in the day, you draw atoms kind of like this, or you draw like a little circle and there'd be 2 dots, and that was supposed to represent the first energy level having 2 electrons. And then the second energy level could take up to 8, and we always kind of drew them paired together. In this case, we're only going to need 7, so that we have a total of 9. So here's a beautiful model of a fluorine atom, which is grossly inaccurate, but I can deal with it. It gives us a nice distribution of the electrons. Do you remember, too, now that we've gone through a first-year course, we know a little bit more about atomic structure. The electrons are paired because they're paired together in orbitals, and there are a certain amount of orbitals available per energy level, and that's why we get the 2 in the first energy level and 8 in the second. We'll all get into that when we look closer at atomic structure. Let's say I want to bond 2 fluorine atoms. So I'll draw another fluorine. And then he's got 7 valence. And I'll kind of do this as a mirror image. 7. So here's fluorine and fluorine. Fluorine atoms are not stable. They do not have a full outer shell. They're close. Actually, being close makes them highly reactive. We really want to fill that outer shell, and all we need is 1 more electron in each fluorine atom. In this case, transferring an electron doesn't satisfy both atoms. So with fluorine, we share that pair in the center. That shared pair of electrons counts for both fluorine atoms. So they both have a full shell of 8. Covalent compounds are usually formed between nonmetals. In this case, we should make note, we will have no ions formed. And I may be jumping the gun a little bit by using this word ion. Ions are charged particles that result from the transferring of electrons, either gaining or losing electrons. We're not going to have that in this neutral fluorine molecule, F2. We're sharing. We're not gaining or losing. That shared pair spends an equal amount of time by both fluorine atoms. So we acquire no charges on the fluorines, which is a little bit different from the ionics. In an ionic compound, we're going to transfer electrons, and that will form charged particles. So let's say we've got, how about sodium? Sodium's not going to be too crazy. Sodium's element 11. So we got the 2. And if we put 8 in the second energy level, that gives us 10. There's one more for 11. Here's sodium. Sodium atoms are neutral. They would have 11 protons in the nucleus, which we don't really care about the protons when we talk about bonding. We're concerned with electrons. But we are not stable. We only have 1 electron in our outer shell. We would like a full outer shell, which usually means 8. Let's bond this with a fluorine. So the fluorine had 9. 7 in the second energy level. Cool. Fluorine. So we want to find a way of giving both atoms a full outer shell. Sharing would be okay for the fluorine. He could get a full shell. He really only needs 1 more. But it doesn't do a whole lot for sodium. And if sodium's sharing, he goes from 1 to 2. But he's really looking for a full shell of 8. So here's a situation where the transfer is a better option. Since sodium only has 1 valence electron, ooh, I dropped another vocab term, valence electron being the electron in the outer shell, let's just get rid of it. Let's just give it to the fluorine. Fluorine can gain the electron, fills his outer shell with 8. Sodium can lose that 1 electron. Now his outer shell becomes the second, and the second is filled with 8. Match made in heaven. This is the ionic bond, where we transfer electrons. We're going to form charged ions. This usually occurs between metals and nonmetals, and 99% of the time it's the metal that'll lose the electron and the nonmetal that'll gain. Now when we talk about forming a charge, it's all about a balance between protons and electrons. So let's look at atoms versus ions. If I have a sodium atom, sodium atoms are element number 11. So we're going to have 11 positive protons, and we'll have 11 electrons. I won't put the neutrons in because they're neutral. So this gives us no charge, but the atom was not stable. So by losing that last electron and forming a sodium ion, we are now stable, but we are not neutral. We still have 11 positive protons, but I lost 1. So now we're down to 10, leaving us with an overall charge of +1. A misconception. Some people will think about this whole ion thing as adding and subtracting electrons. So they'll say, ooh, we just subtracted an electron. The charge is -1. We lost an electron. That's like subtracting -1. Ah, danger. No, it has nothing to do with adding and subtracting. It's all a balance between protons and electrons. We will never change the nucleus when we form a chemical bond. So that 11 protons, that's set for life. It's the electron count that changes. So we'll match the balance, we'll kind of balance the count of protons to electrons. That's how we get our overall charge. Fluorine. I kind of mentioned the fluorine atom earlier. Fluorine was number 9. We had 9 positive protons and 9 negative electrons for a total charge of 0. But now as a fluorine ion, that is not the case. We still have the 9 protons, which I didn't draw on this picture because they're not really involved in bonding. But we gained an electron, so now we have 10 negative electrons, leaving us with a balance or a charge that's overall -1. And so again, a danger is people will say, you added 1 electron. Your charge is +1. It's not really about adding and subtracting electrons. I mean, yeah, that's what we did, but to get the charge, we have to think about it it as a balance. It's a balance between positive protons and negative electrons. And if I'm not changing the proton count, if I'm adding negative electrons, my overall charge will be negative. So we kind of hit a lot of these vocab terms. We talked about the difference between atoms and ions. The positive ions are sometimes referred to as cations, a general term for any particle that has lost an electron, leaving you with extra positive protons. The negative ions are also called anions. These are the guys that have gained electrons and acquired an overall negative charge. Sometimes I kind of remember it. And it's a little cheesy, but I really like cats. So I think about cats. They're always happy. There. Here's my positive cation. And the anion, that's a little bit more of a stretch. I couldn't think of anything too creative. I think about like a bug or an ant. We'll make it a happy ant. There we go. He's got like a long negative body. There. Now if you can come up with something better, go crazy. But this helps me remember the difference between cations and anions. They are vocab terms that'll come up throughout the course, and they're very general. A positive ion is sometimes referred to as a cation, and a negative ion is an anion. So down at the bottom, we also, I think, kind of refer to a lot of these terms too. The valence electrons are the electrons in the outermost energy level. These are the most important electrons. They're the ones involved in bonding and chemical reactions. All of the inner electrons, or core electrons, are electrons that are paired in an orbital, which is a good thing. They're all in full stable energy levels. It's just the outer level that may or may not be full. So we're not concerned with inner core electrons, just the valence electrons. We also kind of mentioned the magic number 8. It's called the octet rule. Atoms usually want to gain, lose, or share valence electrons to get a stable outer shell of 8. Now, there are some exceptions. There are some atoms that will follow a duet rule. Well, this sounds cute. This is going to be like hydrogen, helium, lithium, small atoms. Hydrogen's only trying to fill the first energy level. And if you recall, the first energy level only holds 2 electrons. Hydrogen only needs 2 to have a stable outermost energy level. It'll just be the first energy level. Helium actually is stable. Helium has its first energy level filled with 2 valence electrons, and that's all the first level holds. Lithium has a total of 3 electrons. 2 of them in the first energy level. His 1 valence electron in the second energy level. It's easier for lithium to lose 1 rather than gain 7 and try to fill that second energy level. So lithium will usually lose 1 valence electron, bringing him to a full first energy level, which only holds 2. So some of these real small atoms will follow a duet rule, where they're stable with less than 8. They only need 2 valence electrons to fill the first energy level.